So today we're covering 6.1, which is the area between curves. So essentially, you have, here's a drawing right here. Here's a curve. Here's a couple of curves. The first, this one in kind of brownish color is y equals 5 e to the x. And this one that's kind of blue right here is 5x e to the x squared. Okay, and the idea is what's the area of the shaded region, this blue shaded region. And it's really important, these two curves intersect at the point 1, 5e. Okay, so that's an important piece of knowledge. So basically, there's two main ways to looking at areas between curves. Okay, so the first one, well, it kind of depends on what you have. So in this situation here, if you look at these curves and you choose a point here on this boundary and you go vertically to that, then you have another point there. So every vertical line between 0 and 1, between x equals 0 and x equals 1, every vertical line will go through the bottom, will go through, and if you intersect that with the shaded region, then that creates a line segment that whose the bottom is 5x e to the x squared and whose top is at 5 e to the x. Okay, every single thing I got. And so that means that we're going to go with this first option. And what this means is you're going to take the function on the top minus the function on the bottom. And you're going to integrate from x equals 0, or x equals a, to x equals b, over the whole range of everything. Okay, so applying this first equation to finding the area, we're going to integrate from 0 to 1 because x equals 0 is this boundary, x equals 1 is over here. So that one goes there. And then 0 here, this is x equals 0, and that's going to go on the bottom. Okay, and the function that's on top is 5 e to the x, and the function on the bottom is 5x e to the x squared. Okay, so we just need to find that integral, and that will be the area of the shaded region. Okay, so the antiderivative here is if you take the derivative of e to the x, you're going to get the e to the x. So just put a 5 there, and there's that. This one is, we would use the substitution rule. Once you do the substitution rule a bunch of times, then you start seeing patterns, and you start thinking things like this, okay? So if I take the derivative of e to the x squared, I'm going to get e to the x squared times the derivative of this top part, which would be 2x, okay? But this is a minus 5x. So if I take the derivative of this, I get 2x, but I want to make it so that it's minus 5x instead. So if I just do that, I divide by the 2, and I multiply by minus 5. Then, when I take the derivative of this, I'll get this, which is e to the x squared, times x squared, no, 2x. I'm sorry, 2x. So the 2 will cancel with that 2, and now there's my x right there, and then I have the minus 5. Okay, so that's going to be it. And then your limits of integration are from 0 to 1. So from 0 to 1, plug in a 1. That's 5e to the 1 minus 5 halves e to the, that's also e to the 1. Okay, now subtract and plug in zeros. Okay, 5e to the 0 is, I'll just put e to the 0. And then this is also going to be 0, so minus 5 halves e to the 0. Okay, so this right here is actually, just put a 1 there. So e to the 1 is just e. And 5 minus 5 halves is just 5 halves. And then these are going to be, that and that are both going to be 1. And so here is 5 minus 5 halves is also 5 halves. So wait, this is 5 halves e, sorry, minus 5 halves. And that's the area right there. So 5 halves e minus 5 halves. Okay, now let me just say a few things about this other formula. This other formula you're integrating in y. So this is a good example for using this formula. This formula would be if you had a situation like this. I'll just draw a little picture. And here, this one is the right, on the right, and this is left. Okay, and I'll show you what I mean by that. Okay, so let's suppose that we have two equations. Well, this is kind of really bad drawing. Okay, so let's suppose if we go, let's call that C. Okay, so let's suppose, so there would be a situation like this where we want to find this kind of an area right here. And let's say this function on the right would be x equals f of y. And this function on the left would be x equals g of y. Okay, so in this case, if you draw horizontal lines between C and D, you're drawing a horizontal line. The right boundary is f of y, and the left boundary is g of y. Okay, and then this distance here, from here to here, if this is, let's say if that's y, this distance would be f of y minus g of y, would be that distance there. Okay, so you're multiplying by that distance, and then this is like the tiny width, represents the width. So you're thinking, well, these little rectangles here between C and D, and that's what that represents, and integrating from C to D. Okay, so those are the two situations. Okay, now let's do some more practice. Okay, this right here is actually the second one that I talked about for integral from C to D of f of y minus g of y dy. Okay, so we can see that this equation of the red one is x equals 4y minus y squared, and the blue one is x equals y squared minus 6y. Okay, so this right here is our f of y, because this is on the right. Maybe I should do that in red. Yeah, let me do that in red. So f of y is 4y minus y squared. And then g of y is y squared minus 6y. Okay, so here's g right here, and then f is the one over here. Okay, and if you draw a vertical line segment, then the right boundary is f, the left boundary is g. So it's f minus g. And the limits, this is going from 0 to 5. This is 5. Okay, so that means that d is 5 and c is 0 from here. Okay, so we can go ahead and write down the integral. Integral from 0 to 5. And then the f is this one. And then the g is this one. So let's see here, that's 4y minus y squared. Distribute the minus, that's minus y squared plus 6y. And it's going to be, let's see, 4y plus 6y, that's 10y minus 2y squared. Okay, integrating that one is going to be 5y squared, because the derivative, you'll have a 2 coming down, which will give you 10. And then this one will be 2y cubed over 3, because when you take the derivative of this, it's 3y squared. The 3 will cancel that one, and there you go. You'll still have the negative 2, and the y squared is there. And that's from 0 to 5. Okay, so when you plug a 5 in, you're going to get 5 times 5 squared minus 2 times 5 to the third over 3. And then when you plug zeros in, you just get 0. That's 0 and that's 0 when you plug the 0 in for y. Okay, so this is 125. 5 cubed is 125. Minus 2/3 of 125. That's going to be 1/3 of 125. Or 125 over 3. Okay, so it is that this is a full 125. This is 2/3 of a 125. So you end up with 1/3 of a 125. Okay, so that's an example of the other kind where you're going when you're integrating in with respect to y. Okay, so let's take it a step further. This one, or what we want to do is figure out which of these curves is first, and then go from there, and then calculate the area. Okay. So typically, when you have two curves like this, one of the things that you're going to do is you're going to set them equal to each other, like that. And this tells you where they intersect each other. Okay, so subtract 4x from both sides, you get x squared minus 7x equals 0. And x equals 0 and x equals 7. They're going to intersect at those values of x. And when x is 0, then this is going to be, then y is going to be 0. When x is 7, y will be 28. Okay, so this is 7, 28. So you're looking at those 2 points where they intersect. Yeah, but all of them have 0, 0 as the intersection point. Okay, what about 7, 28? That's 7 negative something, so that's not right. This one looks like this one looks okay. And these ones are not okay because they're not even, yeah, both these are wrong because they're not even displayed in the first quadrant where this should be. Okay, so this is the only one that it could be, right here. And we know this bottom function is the x squared minus 3x. And this top function is y equals 4x. And we found that this point is 7, 28. And the most important thing at this point for calculating now is that we know that this is 7. And here they've shown you a typical rectangle. It's vertical. That means that we're going to be integrating with respect to x. Okay, so the top function is 4x. Bottom function is x squared minus 3x. And you're integrating from 0 to 7, from 0 to 7. Because every value in here, or every line segment from this to this that's in the area corresponds to a value between 0 and 7. And every value between 0 and 7 corresponds to a line segment. Okay, so that's 4x minus x squared plus 3x. That's going to be 7x minus x squared. So I'll go ahead and integrate that. That's going to be 7x squared over 2. This is going to be x cubed over 3. Okay, now we're going to plug in the top value first. So plug a 7 into here. And the 7 into there. Okay, so this is This is 7 cubed. That's also 7 cubed. So 7 cubed is 343. We can also think of it like this. And 1/2 minus 1/3 is 1/6. So that's 343 over 6 would be the answer. Okay, great. Any questions at this point or concerns? Okay, let's move on to the next exercise, number 4. And here, they switched it up here. It's in terms of x equals a function in y. X equals a function in y. And if you set these equal to each other, then let's see, let's pull this y over here and pull the 4 over there. And then divide by 2, and then I'll write it that way. So y is plus or minus 2. So those are the values where it intersects, and then in either case, so when y is 2, x is going to be 0 in either case, and when y is -2, x is going to be 0 in either case. So you're looking at 0, 2, and 0, -3. Those are where they intersect. So it should be here and there, which is not, so that's wrong. These two intersect there and there. These two intersect there and there, so that's good. This doesn't, so this is out. So not throw that one out. Okay, this one, this would be y equals -4 plus y equals x squared, or x, sometimes times x squared minus 2 would be y equals that. So this is opening the wrong way. Okay, so this is the one that we have, and then this makes sense because 4 minus y squared, that would be this one. So you're starting, you're starting at 4, and then you're opening up this way. And then this one, you're starting at -4, and you're opening to the right. Okay, so since this is a positive y squared here, that means you're opening to the right. So that's this one right here. Y squared minus 4. And since this is minus y squared, that means you're opening to the left. So this one is x equals 4 minus y squared. And if you choose a typical value of y, then your right value is going to be 4 minus y squared. The left value is going to be y squared minus 4. Okay, so now we're ready to write down the area integral. And you're going from -2 to 2 because you're going in you're using horizontal. You're adding up horizontal rectangles, or adding up horizontal line segments if you want, whose length is this minus this. And whose width is, you can consider that to be dy. So you kind of think of it that way. It's not exactly, but it's a good way to think about it. Okay, so what's this? 4 minus a -4, that's going to be 8. Negative y squared minus y squared, that's minus 2y squared. Okay, so now we can integrate. The integral of 8 is 8y, and the integral of this one is 2y cubed over 3. And another thing that you could do, and which I think I will do right now, hopefully it won't confuse too many people, is you notice that this area here is the same as that area. So in other words, this area up here is the same as this area down here. They're both the same. So if I double it, and go from 0 to 2 instead of from -2 to 2, but I double it, then I'll get the same result. Okay, so I'm kind of switching halfway. I hope it's not too confusing. Maybe it is too confusing. Yeah, it's probably too confusing. I should not do that this time. I'll go from -2 to 2. Okay, so if I put in 2 here, I'm going to get 8 times 2 minus 2 times 2 cubed, wow, over 3, minus, and then here it's going to be 8 times -2 minus 2 times -2 cubed over 3. Okay, so this is 8 times 2. This is -8 times 2, but it's being subtracted, so it's going to be 16 plus 16, and this will be minus 16 thirds. And that's a minus. You've got like 3 minuses here, 1 there, 1 there. That's 5 minuses. That's minus 16 over 3. Okay, so that's going to be 32 minus 32 over 3. So you got a full 32, and you're subtracting a third of a 32 from it. That means you're going to end up with 2/3 of a 32, or 64 over 3. Okay, now exploiting this idea, what would have happened is you go from 0 to 2, and you're just integrating this, 8 minus 2 minus 2y squared. So instead of going from -2 to 2, you just go from 0 to 2. And you get the same thing. So that's another way that you could do it. You wouldn't get up with this part, you would just double this, which is essentially what happened anyways. Okay, number 5. So region between the curves x equals 6y squared. That's going to be a parabola that opens to the right. And then x equals 20 plus y squared. That's also going to be a parabola that opens to the right. We can check where they intersect. So we subtract this y squared over here. We get 5y squared equals 20. Divide by 5. That's y squared equals 4. And y equals plus or minus 2. So it's going to intersect it when y is plus or minus 2. Okay, now when y is 2, x is, just plug in the first one here, 6 times 2 squared, which is going to be 24. Wow. And when y is -2, it's the same thing. Because when you plug a -2 in here, you get -2 squared, which is positive 4, times 6 is 24. So you're looking for 2 points of intersection, 24, 2, and 24, -2. Okay, so 20, wait a minute. Yeah, it looks like right here and here on that one. And this one's off because it should come over this way, so that's not. And this one's going, these are both wrong. Because this is a parabola that opens to the right. This is also a parabola that opens to the right. These open up, and that opens down. This opens to the left. This is the only one that opens there. So I guess we could have just figured out from there as well. Okay, but that's fine. Okay, now, this right one here is x equals 20 plus y squared. This left one is x equals 6y squared. Now again, we have symmetry. Which means that this top part area is the same as the bottom part area. Okay, so this area, we'll call that 1. area 1 equals area 2. Okay, so let me go ahead and set the integral up and show you how this interacts. Okay, you're going to integrate from, and now it's important, these have to be y values, okay? And this is until you draw like horizontal line segments, because you have to go from, because you have to use this boundary and that boundary. So you have to use this boundary, 6y squared and 20 plus y squared. Okay, this is the right one. The left one is 6y squared. So those are the boundaries that we're going to use. Now, these limits have to be in y, and this goes from, so you have line segments down here all the way to -2. So you should go from -2 up to 2. So -2 all the way up to 2. Okay. So from there to there, this is what you're looking at. This is the boundaries right here, from -2 to 2. And that's what your limits of integration you have to use. Okay, it's kind of confusing a bit, but you know, maybe if you think about it for a long time, then it becomes more and more clear. Okay, now, because of this, then you can double it and go from 0 to 2. Okay, because these two areas are the same. So instead of going from -2 to 2, go from 0 to 2 and double it. Okay, so double it right here and go from 0 to 2 instead of -2 to 2. This inside part is 20, and you have plus y squared minus 5y squared minus 6y squared. So that's going to be 20 minus 5y squared, like that. Okay, integrate 20 and you get 20y. Integrate this one and it's minus 5y cubed over 3. Okay, and that's going from 0 to 2. Okay, so plug a 2 into here. So that's going to be 20 times 2, which is 40. And then minus, what is it, 5 times 2 cubed. Oh, this is interesting. We have the same kind of thing again. So this is 40 minus, okay, this 2 cubed is 8. 8 times 5 is 40. So you have a full 30 minus a third of, a full 40 minus a third of a 40. That means you're going to end up with 2/3 of a 40. Okay, so 40 times 2 is 80, times 2 is 160. And you get, for the final answer, you get 160 over 3. Okay, let's go to the next exercise. Or we'll pause there for a second. Okay, so now next exercise introduces another concept. And let me explain. Okay, so you want to sketch the region enclosed by this curve and this curve from 0 to pi, from x equals 0 to x equals pi. So each of these graphs goes from 0 to pi. Pi is a little bit more than 3, so it looks like it's going from 0 to pi. Each of these is going from 0 to pi. We need to figure out which one it is, though. Again, one thing that you can do to help you is to set these equal to each other. Eventually, you need to figure that out anyways. Okay, so let's see. This 5x can go over here. So that becomes 10, 5 cosine x. So that's 10 cosine x. equals 5. Divide everything by 10. So now it's, where is the cosine 1/2? And, well, let's see here. It would be this kind of a triangle where you have 1, 2, root 3. So here the cosine is 1/2. And this angle is pi/3. Okay, so x equals pi/3. Also, you'll also have another angle over here. Wait, that's negative 1/2. So that's not going to work. No. So this is the only one in between 0 and pi. This is the only one. Okay, this is the only one. This one is negative 1/2. Okay, so that's not going to give it to you. Okay, so that one's negative 1/2. Okay, so that's the only one, pi/3. This is the only place where they're going to intersect, which should be about 1/3 of the way through. And so these two are the only ones where they do that. So that means we can rule these two out because these intersect in 2 spots. Okay. Maybe this looks cooler. Maybe this graph looks cooler, but no, it's not right. Okay. So which one of these is it? Well, there's a couple ways you can figure out. The other one way is we can take this pi/3 and we can figure out what we can use. Maybe you can plug that pi/3 into the first one. And since cosine pi/3 is 1/2, that's going to be 5/2, right? So that means that draw this better. So that means that this point right here, pi/3, comma 5/2, has to be on the graph. And this looks like it is right here. This is negative right here, so that can't be it. It should be up here. Okay. That's one way to figure it out. So this is the graph anyway, but that's one way to figure it out. Another way you could figure it out is maybe look at this first one. This is 5 cosine x, which basically means it's gonna, when x is 0, you're gonna be up at +5, right? And you need to come down like that. So this graph right here, this one right here, and I'll mark this one in red. Okay, this graph is y equals 5 cosine x. Okay, and then this graph, I'll mark that in green. Okay, when x is 0, this is 1, which makes this -5, 5 minus 5, which makes it 0. Okay, and that comes up like that. Oh, this is Christmas colors. Okay, let's see here. Maybe we could make a mathematical Christmas ornament from this. Okay, so this one is y equals 5 minus 5 cosine x. Okay, so this number 6 represents another concept that I wanted to discuss, that we need to discuss, and that is here you want to find these areas right here. Well, for this area, the red curve is on top, the green one's on the bottom. But then it switches over here. So what you have to do is you have to do 2 integrals. Okay, so the first integral goes from 0. So this is 0. Here's pi/3. So the first integral goes from 0 to pi/3. That's number 1. And you have to have the red curve on top. And you subtract the green one from it. Dang, there's not enough space here. Subtract this one. That's the first area. Then you have to add the second area to it, which will go from pi over 3 to pi. So this is pi right here. So now we're going from there to there, from pi over 3 to pi. And you have to have the green one on top. And subtract the red one. Okay, so the total area will be the sum of the two areas. The sum of the first area plus the second area. Okay, so let's go ahead and use the first area again. So 5 cosine x plus 5 cosine x. That's 10 cosine x minus 5. Again, that's the first area. Second area, you have a 5 minus 10 cosine x, like that. Okay, let's go ahead and take an antiderivative. 10 cosine x. Well, 10 sine x. If you take the derivative of sine x, you get cosine x. So that's the antiderivative of that part. And then minus 5x. And that's going from 0 to pi over 3. And then we kind of get the opposite over here. This is 5x minus 10 sine x. And that's going from pi over 3 to pi. Again, this is area 1. This represents area 2. This is area 1, represents area 2. Okay, but we're putting them all together though, so that doesn't matter. So if you put a pi over 3 in here, we get 10 sine of pi over 3 minus 5 times pi over 3. So putting a pi over 3 in here gives 5 pi over 3. And then when you subtract and put a 0, and that's 0, that's also 0. So that's good. Okay, now the second part, switch colors for that. Put a pi in, that's 5 pi, minus 10 sine pi. Okay, now you subtract and put the pi over 3 in. So 5 pi over 3 minus 10 sine of pi over 3. Okay. You can plug in, okay, sine pi over 3 is where we have pi over 3 over here. The sine is root 3 over 2. So 10 root 3 over 2. This is minus 5 pi over 3. This is 5 pi. That's going to be 0. Sine pi is 0. Sine of pi is 0. And then you have minus 5 pi over 3. And then a minus, that's 10. That's plus 10. And again, sine pi over 3 is root 3 over 2. Okay, well, darn it, we ran out of space. So I guess maybe we should just end right there. But no, we have to keep going. Okay, so let's finish it over here. Okay, so if you combine this one and this one, then you just get 10 root 3. And if you combine this, this, and this, then you basically have 5 pi over 3, which is 3/3 5 pi over 3, and then you're subtracting a third, so you're going to get 5 pi over 3 plus 5 pi over 3. Okay, and then this will be the answer. Okay, let's go to the next one. Number 7. Yeah, so I guess the concept here was that when it switches who's on top, who's on bottom, then you got to switch the integrals. Okay. And number 7 is yet another concept that we'll explore here. So here we have 3 different curves. You've got y equals 3 over x. You got y equals 12x. And you have y equals 1/12 x. Okay, so 12x, what that means is that's pretty steep. So it's, I mean, if you're looking at each of these graphs, then this line that goes up really steeply, that's a good candidate for your y equals 12x. And as it goes over 1, it should go up by 12. So this should actually be way up here. Yeah, so it goes through 0, 0. Okay. So all those are correct as far as that's concerned. But at 1, okay, this is 2 right here. So 1 is about right here. It should actually be up at 12. And it's not. So this one's not it. And again, this is 1. It should be up here. It should be up at 12 up here. So that's not it either. Just based on just that alone. Okay, now this one, here's 1 right here now. And this does look like it's up at 12. This does, because this is the curve right here. So that does look like y equals 12x. This also looks like y equals 12x right here. Okay, and then likewise, this curve here, it has a really shallow slope. So that would be y equals 1/12x, which looks like this would be y equals 1/12x as well. And then this red one, y equals 3 over x, that goes down like this. It doesn't do this, so this is off. So that means that graph's wrong. This is y equals 3 over x. Okay, so now let's try to work on setting up an integral. And what we should do is first figure out what these intersection points are. Okay, so what's this point right here going to be? It looks like it's at 6. So let's go ahead and set those equal to each other, and we'll see if that's actually the case. Okay, so 3 over x equals 12x. We're intersecting these 2 graphs. This x comes over here, and you get, and the 12 comes over here, so you get 3 over 12 equals x squared. So x squared is 1 over 4. So it's x equals plus or minus 1/2. But we know in the first quadrant, so it's x equals 1/2. So that point is 1/2, comma, and then if we plug a 1/2 into here, we get 6. Okay, so that's 1/2, comma 6. Is this point right here. Okay, now let's figure out what this point is. That also looks like it's at 6, but we'll try to make sure. Or x equals 6 rather than the y equals 6 that we have here. So we're going to set those 2 equal to each other. No, not those 2. Whoa, I'm way off on the colors. Let me do this in blue instead. It's this one and this one. Okay, so the x goes over here, and the 12 comes over here, so we have 36 equals x squared. So that means x equals plus or minus 6, but we know it's got to be in the first quadrant over here. So x equals 6 is indeed the one. And if we plug it into here, then we get 1/2. Okay, so this right here is 6, comma 1/2, that point there. Okay, now, I'm going to, so remember this is 1/2 6, this is 6 1/2. I'm going to go to the next page because I made it bigger on the next page, so you can kind of see what's going on. Okay, so we have this point right here. This is 1/2, 6, and then we have this point here, which is 6, 1/2. Okay, so what you're going to do here is we're going to end, because everything's in terms of y equals, y equals, y equals. So this is, what's this? This is y equals 3 over x. This is, this line here is y equals 12x, and then this line down here is y equals 1/12 x. Everything's y equals. So we're going to integrate in x, okay? Now, in this case, what you have is if we, so here's 1/2 right there. If we drop a vertical line segment down right here, then if you look at this part of the region, we'll call that 1. We'll call this one 2. Okay, so if you look at region 1, the function that's on top is this 12x. This one's on top. And the function that's on bottom is this 1/12 x. Okay, so the top is 12x, the bottom is 1/12 x. Okay, for this area, for region 1. And you're going from 0 to 1/2 in x. So from 0 to 1/2, 0 to 1/2 x. Top function is 12x, the bottom one is 1/12 x. That's area 1. For area 2, this is the top function right here. This is the top one for A2, and this is the bottom. So still, this 1/12 x is still the bottom for both of them. And this is going from 1/2 to 6. Okay, so we're going 1/2 to 6. Top one is 3 over x. Bottom one is 1/12 x, so our x over 12. Okay, so those are the two. So this first area is this integral. The second area is this integral. Okay, so let's go ahead and figure that out. If you integrate this, you're going to get 6x squared. Okay, because you take the derivative here, you have a 2 coming out, which 2 times 6 is 12. So they get that one. And this is going to be x squared over 24. Because if you take a derivative here, you'll have a 2 come out. This will reduce back to a 12. And that goes from 0 to 1/2. Okay, then over here, this one, integrate 3 over x, that's 3 times the natural log of x. This one is x squared over 24. And that's going from 1/2 to 6. Okay, plug in 1/2 here, and you have 6 times 1/4, so that's 6 over 4. And this one is going to be, whoa. So 1/2 in here, you're going to have 1 over 24 times 4. Because 1/2 squared is 1/4. So you get this. Okay, then here you plug in a 6 in here, you get 3 times the natural log of 6 minus, and then plug a 6 in here, you get 36 over 24. Okay, then subtract and plug in a half. So that's 3 times the natural log of 1/2. And then minus, and then here you have, you plug in 1/2 into here, so that's 1/4. So that's minus 1 over 24 times 4. Lots of weird stuff going on here. Okay. So it turns out, though, that this and this, okay, this is 3/2. Turns out this is also 3/2. So those are going to cancel. Yay. And it also turns out that this is minus 1 over 24 times 4. We have a minus and a minus. This is actually plus. So those are going to cancel out. Those two terms are going to cancel out. Okay, so that leaves us with only 3 log 6 minus 3 log 1/2. Okay, now using properties of logarithms, where you have the natural log of one number minus the natural log of another, that's the same as the natural log of the first one divided by the second one. So, and that comes up as a 2, so that's 3 log 12.